Ladies and gentlemen, get those pens, pencils, colored pencils, highlighters ready to rock and roll tonight because we're going to do a lot of work. Our topic tonight is vertical stretching and compressing. And ultimately, our goal is to answer this very simple question down here. If you start with a function y equals f of x and you replace it with y equals k times f of x, and that's how we're going to pronounce it, k times f of x, what effect will that have on the graph of the original function f? And what you'll notice here in this picture is there's this blue function here that represents the original. And if you multiply that function by a 2, in other words, the value of k equals 2, you'll see this green graph where you notice the relative max got taller and the relative min got lower, and that's what we call a vertical stretch. However, if you look at the red function, the k value is 0.5. And so you follow the red graph and you'll notice the relative max is lower, and yet the relative min is also, well, it's kind of taller, or closer to the x-axis depending on how you want to say it. And that's what we call a vertical compression. So we're going to warm up with a little discovery exercise, and I'm going to start off with the function f of x equals x squared minus x minus 2. And what I did is I put that into my calculator. I went to my table of values, and let me show you what my table looked like. I hit a 0 at -1, y-intercept of -2, and let's see, another 0 at x equals 2. And I'm going to go ahead and I'm going to graph that function. And we get a nice parabola that kind of looks like this. So its vertex is going to be right around x equals 1/2, and it's going to turn around and bounce back up like this. Now here's the ultimate question. Here's what we want to ask ourselves. What happens if I multiply f of x by a factor of 2? So in this case, you'll notice that k equals 2. And I'm going to do a little substitution. For f of x, I'm going to substitute the original function, x squared minus x minus 2. And then I'm going to distribute my 2 to all three terms. So the new function is 2x squared minus 2x minus 4. And what I did now is I put that new function into my calculator, and I made a little table of values for him, and it turned out like this. And I was using the same x values just to be consistent. And I want you to really focus on these y values. Compare the y values from each table and ask yourself what's happening to the y values as we go across. And I'm going to go ahead and I'm going to graph this raspberry function here. And so I got my points all plotted, and I'm starting to connect them now. And I don't know if you've ever played with silly putty in the past, but this is basically like a piece of silly putty. You're just stretching it. You're pulling the top up higher, you're pulling the bottom down lower, and you're just stretching out the function. And the question is, what effect did the 2 have on f of x? And what you'll notice is we doubled all the y values. Okay, the x values didn't change, but we doubled all of the y values. Our second discovery exercise, we're going to start off with the exact same original function. So part A is exactly the same, and I imported the same table of values. So I'm going to work on plotting those points. And then we can already start to ask ourselves, what's going to happen if I multiply this function by a factor of 1/2? And we'll see how well I can connect these dots here. Relative min at x equals 1/2. Okay, so here we go. They want me to take the function f of x and multiply it by a factor of 1/2. So I've got my 1/2, and I'm going to substitute the original function, x squared minus x minus 2, and I'm going to distribute that factor of 1/2. We're going to distribute to all three terms. So I get 1/2 x squared minus 1/2 x minus 1. And what I did is I entered this into my y equals on my calculator, and I generated a new table of values. And let's really focus on the y values, asking ourselves what's happening to each y value if I compare the two tables. And what you'll notice is that each y value basically got cut in half. And so I'll plot these new points the best I can. And this new graph is going to be a little bit shorter. In other words, each point, for instance, this point's half as tall as the original. Again, this point's half as tall as the original, and the same could be said for all of these others. Notice the one thing that doesn't change is the location of the x-intercepts, or these zeros. Of course, half of 0 is still 0, so those points didn't change. So let's see if we can kind of generalize what we just discovered in those two exercises. Again, if y equals f of x is replaced with y equals k times f of x, what effect will that have on the graph of f? And right off the bat, if k is bigger than 1, it's going to be a vertical stretch by a factor of k. However, if k is a smaller number that's greater than 0 but less than 1, now it's a vertical compression by a factor of k. So you're either stretching or squishing the function. And here's a new one that we haven't seen quite yet, but we're going to give it to you anyway. If k is negative, it's a reflection over the x-axis. Alright, so we're going to get a little practice with that tonight. So just watch out for negative k values, and that's going to be a reflection over the x-axis. Okay, so let's summarize everything we've done up to this point. Here's the number one thing we need to know, and I think this is really going to simplify everything for us going forward, is vertical stretching and compression only affects the y coordinate of the original point, and it does not, I repeat, not affect the x coordinate. And just to convince yourself of that, you can go back and compare those table of values we generated during the discovery exercise, and you notice how in those tables the x values stayed the same, but the y values either got doubled or cut in half. So let's look at understanding k's impact on f of x, and here we go. If y equals f of x is replaced with y equals 3 times f of x, so now I've got a k value of 3. What effect does that have? Well, first of all, right here we're asking ourselves, is it a vertical stretch or is it a vertical compression? And we said anytime the k value is greater than 1, it's a vertical stretch. So every point's going to get a little taller or a little further away from the x-axis by a factor of 3. In our second one, because our value of k is it's greater than 0 but smaller than 1, we're going to call it a vertical compression. In other words, every point's going to get a little shorter, or we could say every point's going to get a little closer to the x-axis, and it's a vertical compression by a factor of 1/4. Now here comes a little extra curveball here in number 3. Notice how your k value, we've got a k value of 4, but it's being negated. So here's what we're going to say. First of all, and let's make a note, k is equal to 4 here. It's a vertical stretch by a factor of 4, followed by a reflection over the x-axis. And that's all we got to watch out for tonight. We're going to sprinkle in some negatives, and we just automatically say it's a reflection over the x-axis. A little trickier here. Let's see if we could fill in the function. So let's see. If we see a vertical compression by a factor of 2/3, that means this is your k value right here. So we would say f of x is replaced with y equals 2/3 f of x. And that's going to cause a vertical compression. Here's a vertical stretch with a factor of 6. So right there, we're saying k equals 6. So y equals 6 times f of x would be the replacement. And our third one says we had a vertical compression. Whoops, I got a little typo here. I meant for this to say 3/4. So it's a vertical compression of 3/4, so that's my k value right there. But it also says it's followed by a reflection in the x-axis. So that means we're going to negate k as we type it in. So we got y equals negative 3/4 times f of x. And that would get it done. Now as we tackle these three examples, keep reminding yourself, and hopefully we're going to sound like a broken record here, that these the factors of k, this vertical stretching and compressing, they don't affect the x-coordinate. So what's going to happen is my x value is going to stay or remain a 3 throughout this entire process, but it's only going to affect the y-coordinate right here. So we're saying if the point 310 lies on the graph of f of x, identify a point that lies on the following functions. So what do we got here is we got a factor of 4. In other words, we've got to multiply this y-coordinate by 4, so I'm going 3, 40. We're stretching it out, and it's going to get a lot taller. Here, we're multiplying by -2, so it's 3, -20. And here we're multiplying by a factor of 1/2, so it's 3, 5. And again, just to recap that, I multiplied the y-coordinate of 10 by 4, by -2, and by 1/2, and that's all I did. Okay, now we're going to put multiple transformations on your plate and see if we can sort them out. And the order is going to be very important. So just think about, well, if f of x is replaced with y equals 6 times f of x plus 12, think about your order of operations and how you would evaluate this function. The first thing that would happen is we'd multiply f of x by 6, okay, followed by adding the 12. So let's talk about the multiple of 6, then we'll talk about the 12. So we can say that we've got a vertical stretch. And again, I'm saying stretch because this number is greater than 1. Stretch of factor 6 followed by a vertical shift up 12 units. Now the second one, we're going to go vertical compression because I had a k value of 3/4, and that's smaller than 1, of factor 3/4. Followed by a reflection over the x-axis, and that's automatic because of the negative, followed by a vertical shift down 5 units. Okay, so now when we say that f of x has a y-intercept of 15, what we're really saying is that there's a point called 0, 15 that lies on that graph, and we want to find what is the y-intercept of the following functions. Again, we're going to stress the same principle. The x value will not change tonight. It's all about manipulating the y value. So but we got to follow our order of operations. So in example number 1, we're going to multiply by 2 first. And after we multiply the 15 by 2, then we'll add the 15. So it really becomes, if I multiply by 2, it's a 30, add 10, it becomes a 40. So just recap, multiply by 2 first, then add the 10. And that order is going to be followed every time. Now in the second one, I'm going to multiply by 1/5 first. And that makes the 15, and again, feel free to use your calculator, 15 times 1/5, that'll turn it into a 3. And then I'm going to subtract the 2 after that, so it's a 1, 0, 1. Our third one, let's multiply the 15 by -3, and that's going to make it -45, and you can even put a little note here to yourself, -45. Then I'm going to add this 20, and that's going to make it a -25 by the time I add it, so 0, -25 would be my y-intercept. Here's a new question worded a little differently. It sounds scarier, but really it's the same thing what we've been doing. We said we got a function with a range of -4 to 6, so what they're really saying is that your y-min is -4, and we don't even care what the x value is tonight because it's not going to change anyway. And your y max is a +6, and so we're just going to manipulate those two values. So what I'm going to do is I'm going to start with my y min, and I'm going to multiply my y min by 3 and then subtract 6. So if I multiply -4 by 3, it's a -12, subtract 6, it's a -18, so my range is going to start at -18. Now I'm going to work with my y max, multiply it by 3, and it turns into an 18. And if I subtract 6, it turns into a 12. So there is my new range. All right, we'll do the same thing here with this next one. Start with your y min and multiply it by -1/2, and that's going to make it a +2. Add 5, and you got 7 for your y min. Now we'll manipulate the y max. If we multiply by -1/2, that turns into a -3. If I add 5, it turns into a 2. So 2 is my new y max on the range. This group might be my favorite ones, and basically we're given an original function and we're going to write a new equation that represents y equals 3 times f of x plus 10. So basically instead of manipulating a single point like we've been doing for the past few minutes, we're going to manipulate the entire equation. So here's the deal. We're going to take this entire function and I'm going to substitute it for this f of x. So it's really, I'm going to say y equals 3 times 2x squared minus 6x plus 7. And then of course plus 10. I know it sounds scary, but watch how easy this is. We're going to distribute the 3, and it's going to be 6x squared minus 18x plus 21. And then of course we got the plus 10 here. And now I'm just going to finish by combining like terms. So it's 6x squared minus 18x plus 31. And what you notice is if I graphed this function and then I graphed this function, every y value, you'll see it get multiplied by 3 and then shifted up another 10 units. So it's a vertical stretch by factor 3 and a vertical followed by a vertical shift up 10. All right, let's do, we're going to follow a similar process. So I'm thinking y equals 3 times, substitute the function, -x squared plus 5x plus 11, and then there was a plus 10. So again, I'm just substituting this function into this f of x right here. And let's distribute the 3 and then combine like terms. Y equals -3x squared plus 15x plus 33 plus 10. And then we'll combine those two terms. And I tell you what, if you want to get real brave and live on the edge and you want to combine this into just one step, if you feel comfortable doing that, I'm okay with that. Very similar process here, but I want to remind you there is an invisible -1 right here, and so I'm going to take this equation, I'm going to substitute it in for f of x right here, and I'm going to really stress the invisible -1, because what's going to happen is that invisible -1 needs to get distributed throughout the entire function. So now it's a negative 6x squared minus 2x plus 3 minus 5. And just while we're doing it, ask yourself, what effect did that have on the original function? And again, it caused a reflection over the x-axis, and then after we reflected it over the x-axis, we shifted everything down 5 units. Let's try one more function that way. So we're going to take this original bear and substitute it for f of x right here. We've got a -1 followed by our substitution. And I'm using square brackets tonight, but as always, it's the same thing as parentheses, so you can use whatever you're comfortable with. And I'm going to distribute that. So a -1 times a negative x squared is positive x squared, positive 3x minus 4. And then I'm going to finish by combining my like terms, and I get a -9 for my third term. Just to recap what we've done so far tonight, we've talked about manipulating a specific point. We've talked about manipulating the range. We've talked about manipulating an entire equation like we just did in the last 2 slides. And now we're going to finish the night by talking about manipulating a function. And these might be the most enjoyable ones where you get to plot these points. And so with this first function here, just tell yourself we're multiplying every y value by 2. Multiply every y coordinate by 2. So here's what we got cooking. This point right here, right now the y coordinate's -4. If I multiply the y coordinate by -2, it's going to put me at -8, which is, boy, that spills off my graph paper a little bit. Let's see if we can squeeze in. So that would put me right here. This y coordinate's +2. If I multiply by 2, I get 4, and the 4 turns into an 8. So we're going to spill off. And I think this happens on our sheet tomorrow a little bit, where we have to improvise and just kind of estimate where that point is off the graph. And so that would be the new function. I'll switch colors here. If I multiply everything by -2, it's going to stretch it by a factor of 2, but it's also going to reflect it over the x-axis. So this -4 turned into a +8. I'll estimate it right here. This +2 turned into a -4. And this +4 turned into a -8. I'm going to estimate it right there. And so you can see how the reflection over the x-axis looks when we get it graphed. The last one I've got cooking, and I'm going to have to change colors here. Now I'm going to multiply every y coordinate. Again, I'm looking at the original function. I'm going to multiply by half. So this -4 turns into a -2. This +2 turns into a +1, and this 4 turns into a 2. And this is what a vertical compression looks like. We kind of squished the function down, and it got closer to the x-axis. Alright, more practice here. We're going to look at the original y values, and we're going to multiply every y value by 1/3. And if the values get a little messy, we're just going to estimate them the best we can. Now this 6, if I multiply by 1/3, is going to turn into a 2. This -2 is going to turn into -2/3, which is just about right there. And then this 3 is going to turn into a 1. And so what we get, again, this is a vertical compression. It got squished closer to the x-axis. Number 2, we're going to multiply every y coordinate by a -1, and then we're going to add 2. So we're going to do 2 things. So first things first, this 6 is going to turn into a -6, but if I add 2, it turns into a -4. I know, so I tried to do 2 things at once there, and I hope it didn't go too fast. Start with -2. We're going to multiply by -1, which turns into a +2, and then add 2 more, so we're at 4. And then last but not least, we've got a 3. We're going to multiply by -1, and then add 2, which should make it a what? Yeah, I think it's going to make it a -1. So my new function is going to look radically different. It got reflected over the x-axis and then shifted up 2 units. Well, we finally made it to our last slide. It sure was a very long lesson tonight, so congratulations on persevering and getting through it tonight. But we'll go ahead and we'll wrap this bear up. Now we're working with a parabola, and again, they're just asking me to multiply every y coordinate by a 2. So we're definitely going to spill off the graph, but these 5s here are going to turn into 10s. 0 stays 0. -3 turns into -6. -4 turns into -8. Let's see, and then we just kind of repeat. -3 turns into -6, 0 stays 0, and this 5 turns into a 10. Make sure the x-coordinates stay the same. So actually my first point, I'm going to cross that off. It should be over here a little bit, and hopefully you were screaming at me while I screwed that up. And again, it's going to just, the graph got a lot taller, and we call that a vertical stretch. Our very last one for the night, again, we've got an invisible -1, so I'm going to multiply every y-coordinate by a -1, which means my 5 turns into a -5. My 0 stays 0. My -3 turns into a +3. Let's see, +4, +3, 0 stays 0, and my -5, or 5 turned into a -5. And so now I've got a relative max. What used to be a relative min is now a relative max, and my function looks like that. So again, if the number one thing we need to learn tonight is that these stretching and compressing only affects the y-coordinate, it does not affect the x-coordinate. And if you come to class with that one idea, you're going to be in great shape tomorrow.